Hello everyone and welcome to another video. And abstraction is very important. Almost every single time I make a video there's always a place or two where abstraction pops up because it's just a very relevant thing. And because of that I finally decided that it deserved an explanation of its own. A video with 3 examples of what abstraction actually is to finally once and for all explain the topic. So without any further ado, let's get into it. And let's start with science. Economics is a social science that focuses on the production, distribution and consumption of goods and services. It is a social study because economy would not exist if not for people. So in order to understand economics, you need psychology, the scientific study of mind and behavior, which is just the beginning of our abstraction train, because in order to understand the mind, you have to understand the brain. So we need neuroscience, the scientific study of the nervous system, which in order to understand requires knowledge about basic processes in human body. So you do need biology, the scientific study of life. But what is life? Well, whilst we will not get into that in today's video, it is really often said that life is just chemistry, the scientific study of the properties and behavior of matter, like how atoms interact to create DNA. But what are atoms? Well, to answer that question you would need physics, the natural science that studies matter, its fundamental constituents, its motion and behavior to space and time. Laws of physics are the least abstract definitions of the universe. They govern how atoms should react in chemistry, which rule how they should evolve into biology, where they grow into neurology, where they develop into psychology, from which they build up to economics. The spectrum of science. And so there we go, this tells us about abstraction in science, because yes, science is more of a spectrum than a binary pick your poison sort of thing. And so normally it goes math, cat, physics, chemistry, biology, neurology, economics, or whatever you pick at the end it kind of diverges. But there is a cut, and that's very important. What I've demonstrated you so far is abstraction, don't worry, there will be more examples, but I would really also like to mention where abstraction does not happen, and that's between math and physics. Now, it is really useful to mention that abstraction does not happen there because it's actually really easy to show. Whilst between chemistry and biology, for example, it's really hard to draw a line where chemistry starts and biology ends, between math and physics is really simple. If you are talking about the real world and you're calculating stuff based on laws of physics, then you are doing physics. If you are not, on the other hand, then you're doing math. That's it. So that was a kind of beginning, starter, abstract meta example. Now let's get to the real examples. Let's start with man-made abstraction. Now when it comes to man-made abstraction, then you have to look no further than this video, because you are watching it on a computer using some sort of processor, right? And it just so happens that processors are a great example of abstraction. Why? Well, first let's go over how a processor works. Because you see, inside the processor you have registers. Registers are those boxes that keep in the numbers, and you can do mathematical operations between them. For example, add, multiply, divide, subtract. But there's a problem, because you see, when it comes to those registers, there's really not a lot of them. And I do mean not a lot of them. It's dozen in every modern processor. It doesn't really matter how many cores you have or how many anything. There's just a certain set number of processors, that's the standard, and it's actually really small. But programs really often use a lot of different variables, right? Thousands of variables. So how they do it? Well, they mostly store it in RAM. This may not seem as a surprise to many of you, and some may even ask, so what's the problem? Well, the problem is actually really simple. When you have 2 numbers in RAM, here's what you have to do in order to do just simple addition. Load number A from RAM to a register, load number B from RAM to a register, add those together and then save it to the register. Which is, well, a lot of steps for just some simple addition. And that's exactly why humans added a level of abstraction and created other programming languages, so-called high level of abstraction programming languages. But we can go even further than that, because you see, processors know how to do some simple stuff, for example addition, multiplication, division, subtraction and stuff like that. they don't know how to do factorials, for example. They don't know it because, it's just not the basic thing in mathematics, not a basic function or anything, so it's not actually implemented. But we can create our own factorials. It's actually really simple. You just need a loop and that's it. You just have to loop together and multiply the number by itself, but getting smaller by 1 every single time. Here's an animation because I'm not good at explaining it, and there we go. That's factorials. But in our low programming language, it would take the entire loop to do it. In a high-level programming language, we just have a function for that. We just have a function for factorials. Because who wants to write this every single time when you can just use a nice, neat and tidy function? But if we add even more abstraction, crazy things can happen. For example, graphics cards are complicated. Trust me, I would know. And so displaying an image on a screen is an unbelievably complex task. You would be surprised. But if you want to display an image on a screen in HTML, all you have to do is just this. That's the entire thing for an image. Yeah, so that's abstraction programming languages, but why? You may be asking, why do low-level programming languages exist? I mean, let's be real, it seems as if, the high-level programming languages are great, right? To display an image, all you need is a single line. Well, that is true, but there is a problem. Low-level languages are actually objectively better. They are objectively faster, they are objectively more efficient when it comes to space, they are objectively just better. The only catch is that they are just harder to make stuff in. As I said, in HTML, in order to display an image, all you need is a single line of code. On the other hand, in order to do the same thing in C, you need Vulkan and just massive project with dozens of files and thousands of lines of code, and spend a year on it to crack how dynamically low libraries work, and Vulkan and micromanaged memory and all of this just to display an image. And even then it crashes most of the time, so that's not even actually. So yeah, usually that's the really common theme. High level things are easier to understand, but understanding the low level things
would give you the speed.
Yes, if we knew the position and the state of every single atom inside the brain, we would know everything there is to know about it. We would know how consciousness works, how sentience, intelligence, we would know everything. But knowing that would be very hard. That's why we most of the time abstract things, and instead of studying every single atom, we study cells, and then we move on to bigger things like an organ, like brain. And then instead of actually checking exactly how those neurons are firing, because there's just too many of them, we look at the effects, how people interact with each other, and there we go, the abstraction is being built. First we had a meta example, then we have the man-made abstraction. Is there any abstraction in nature? Now, natural abstraction is not really abstraction that happens in nature. You see, abstraction is a very human term. It depends on how we look at the world, it depends on what we see, and it cannot just happen in nature on its own. That's why natural abstraction is just abstraction that happens without us noticing. And my favorite example of that would be friction. You see, really often in physics classes when you're calculating something, it's really convenient to just skip friction. Because, I mean, you don't need friction for every single experiment, and skipping friction makes your life a lot easier. But there is a problem. Because you see, when you're holding an object in your hand, the same laws of physics that allow you to hold an object are allowing friction to happen. Friction is just this, but on a microscopic scale. So you cannot really eliminate friction without eliminating the ability to hold things, unless you abstract. If you abstract friction to a different thing, to a different action, then really easily you can just delete friction and let holding stuff be a thing. So abstraction is actually unbelievably useful. It happens everywhere, in natural cases, inside mankind's greatest inventions, or even in abstract meta-examples. Because abstraction is everywhere, and I really do hope that this video helped you understand it at least a bit better. That'll be it. Thank you everyone so much for watching, and have a great day. Bye.